Hello and welcome back to Recitation Math 141 Summer 2020. As always, I'm your host Bailey here with episode 16, and we are going to learn about antiderivatives and integral part of calculus. Get it? That's a play on words because integral, and we're learning about the definite and indefinite. In fact, integral, and integral means like important. Ha 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 ha. Wonderful job, Bailey. Thank you so much, my loyal fans. I'm very excited, as always, to be making this video. Antiderivatives are after different. So So we start with differentiation with taking derivatives, and then we look at this process where we go backwards, called very creatively anti-differentiation. And this becomes a huge piece of calculus moving forward. In fact, in the math that I do and that Mackenzie does, I can't speak for Mackenzie, I suppose, with her being on the applied side, but the applied side of mathematics. But most of the calculus which comes up in the work that I do is anti-differentiation and integration. So this is very exciting for me. This is also the biggest theme probably in Calculus 2, which I have TA'd for a couple of times now. So I am so excited to begin this journey into anti-differentiation with you. Antiderivatives and the definite integral are very closely related. And I'm actually so glad that Mackenzie decided to switch up the order of things. So you'll notice we're jumping back to chapter 4 to pick up this antiderivative section. I really like the way that Mackenzie has decided to save that for now, because I think these two sections really go together nicely and go better together than perhaps the way the textbook orders it. So, without further ado, let us do some problems. We're going to do kind of a lightning style, at least here at the beginning. There are lots of really good problems to demonstrate kind of how these antiderivatives and indefinite and definite integrals work. So what we're going to do here is we're going to do a whole bunch of problems at the beginning to find the antiderivative, but I'm only going to do one part of them. Because all three parts of these problems will work the same. Okay, so for example, problem 2 here has 3 parts, but if you knew one of them, then you can use those same ideas to do the other 2. So find the antiderivative when c equals 0. So we're just going to do, for example, 2b here. Basically, these are all going to be pretty straightforward applications of some of these new rules. Shout out Dua Lipa. So I'm going to go ahead and write out the relevant rule and then show how you can apply it in this one example. So I won't spend a ton of time on these first few examples so that we can cover some of the more challenging ones later on. So this first problem asks for the antiderivative when c equals 0 of the function g of x equals 1/9 x to the negative 8/9. The rule, which is going to be important here, is going to basically be the reverse power rule. Okay, so am I going to give it a name? I'm not going to give it a name. But the rule that we need, so I'm going to write my antiderivatives. I'm going to write all of them with this integral form. Okay, so hopefully this notation with the little snaky s here looks familiar to you, either from Mackenzie's videos or from the textbook. This just means the integral, the antiderivative of the antiderivative of f of x is the same thing as the indefinite integral. It's just slightly different notation, and this is what you're going to see more often moving forward, is this integral notation. So if I have the function x to the n, where n is some, I should say n not equal to -1, so n not equal to -1. If n is equal to -1, then this is going to break. But anyways, the way that we integrate this, or the antiderivative of this, is going to be x to the n plus 1 over n plus 1, and we're always going to have this plus c at the end. This is so important, this plus c, okay? So we always want to make sure whenever we have an indefinite integral that we have a plus c at the end. You will lose points for that. I can guarantee it, at least in Calculus 2. I would imagine here in Calc 1 as well. You will lose points if you do not have this plus c. It is super important, so make sure that you remember to put that at the end of all of your indefinite integrals. So if I were to, so kind of basically what we're doing with this rule, raise exponent by 1 and divide by new exponent. By 1, divide by new exponent. So it's kind of similar to the power rule for differentiation. Okay, it's kind of similar, except instead of multiplying by something, we're dividing by something. Okay, so raise the exponent by 1, we go from x to the n to the x to the n plus 1, and then we divide by that new exponent n plus 1. You'll see that this breaks if n equals -1, because then I'm dividing by 0. And that's a special case involving logarithms. So let's apply this rule to our specific function here. So we have the function g of x. Actually, let me just write it this way. I'm just going to go ahead and write it as 1/9 x to the -8/9. This is also important that we put dx at the end of our integrals, or d whatever variable it happens to be. This is super important as well. So all these little notational things do matter. Okay, so what I'm going to do, well, first of all, let me go ahead. Whenever I have a constant inside an integral, I can go ahead and pull it out. Okay, so this is the same as 1/9 times this integral. So now I'm going to apply my rule. I've got 1/9. I'm going to raise the exponent by 1, so x to the -8/9 plus 1, and we'll go ahead and simplify in a minute, over -8/9 plus 1. Remember, I'm going to divide by my new exponent, plus c. Okay, we can go ahead and simplify some of this. So I have 1/9. This becomes x to the 1/9 power on top. My denominator becomes 1/9 plus c. Oh, would you look at that? I've got a 1/9 here, and I'm dividing by a 1/9, so they cancel. And I get x to the 1/9 plus c. So that is this first antiderivative. Next up, in our quick little lightning round to get things started, is going to be part C of problem 4. I'm not going to go ahead, well actually, and in fact, excuse me, in this case, it does say when c equals 0. So actually, we can go ahead and erase these plus c's. Normally, you would need to put plus c. Actually, let me go ahead and do it this way. Let me write here plus c, and then I'm going to indicate c equals 0. So that's why it's going away. So in this case, it is just x to the 1/9, but you will not always be told something like that in the instructions. So again, find antiderivative when c equals 0. All right, so, okay, we'll do it in this one. I should have mentioned, I'm going too fast for my own good. We can check by differentiating, so let me go ahead and do that real quick. So if I differentiate x to the 1/9, then let's see, I'm going to multiply by 1/9, and I get 1/9 x to, and I'm going to subtract 1 from the exponent, and I get -8/9. And sure enough, that's exactly what we started with. Okay. So to check our answers, whenever we're anti-differentiating, all that you have to do is take the derivative of whatever you got. Okay, so here, we got x to the 1/9, so we differentiate it, and you should get back to where you started, and indeed, that is the case. Okay, so that's how we can check our answers. Here, find the antiderivative. Now, this is for c. We have k of x in this case equals negative secant squared of 7x over 6. Now, the rule which we're going to need here is that secant squared of kx, okay, so k is just some constant, non-zero, equals 1 over k times tangent kx plus c. So this is the rule which we're going to apply here. So let me go ahead and set up. I want to integrate or antidifferentiate k of x dx. Okay, well that's just the integral of negative secant squared 7x over 6 dx. I'm going to go ahead and pull this. There's a kind of a -1 out here with this negative sign, right? So I'm going to go ahead and pull that out. And I'm going to rewrite the inside here as 7/6 times x. It makes no difference, but now it helps me see a little bit more clearly. Okay, so I have something of the form secant squared of something times x. So why did I write, this should say the integral of that dx. What I wrote there was terrible notation. Secant squared of kx is not equal to that. However, the integral of secant squared kx dx is equal to that quantity. Okay, so sorry for that terrible notation there. It happens to the best of us. Just make sure that you check your work and catch it whenever you see those little mistakes. Okay, but now I can go ahead and apply this rule. So I still have this -1 out front. So now I'm going to have a 1 over k. So k in this case, it looks like, is 7/6. So -1 times 1 over 7/6 times tangent of kx. So 7x over 6. Again, I'll go ahead and write plus c, but again, we will eliminate this because we are told to assume c is 0. And then we can rewrite this. Let me see. I can, instead of dividing by 7/6, I can multiply by 6/7. Okay, in other words, division is the same as multiplication by the reciprocal. Tan 7x over 6. And there we go. Let me differentiate to check real quick. So if I take the derivative of this stuff, then I'm going to get, let me see. So I have to, so I have this -6/7 times, well, the derivative of tangent is secant squared. And I need to multiply by 7 over 6 by chain rule. Okay, that's just the derivative of 7x over 6. I need to multiply by that times 7 over 6. Well, 6 over 7 times 7 over 6, those two are just reciprocals of each other. So this just becomes negative secant squared 7x over 6. And indeed, that is what we started with. So we get to check this guy off. Great. Next, in the lightning round, 5A. 5A. Can you tell that I'm sick of going way over time in these videos? Find, okay, so same thing, find antiderivative when c equals 0. And it says to do as many as you can mentally, but we'll go ahead and write it out here. Our function this time is f of x equals e to the -21x. So the rule, which is at play here, I've been writing all my rules in blue, but now that I wrote the problem in blue, I'll write the rule in red. The rule which we're going to use here is going to be that the integral of e to the kx dx, that antiderivative is just 1 over k times e to the kx plus c. Now here's how I think about this one, and this demonstrates a very general principle relating to the processes of differentiation and antidifferentiation. So when I take the derivative of e to the kx, I multiply by k because of the chain rule. right? I hope that's something which I know we actually went through at some point and derived a nice formula in one of these videos for the derivative of e to the f of x. So if we have e to the f of x, remember, in general, we have the derivative of e to the f of x is f prime of x times e to the f of x. So in other words, you just multiply by the derivative of the exponent. And so if our exponent is kx, well, then that derivative is just k. So we multiply by k. Therefore, so now, oh my gosh, that looks like a j, not a t. Therefore, when anti-differentiating, okay, so going backwards, we're going to do the opposite of multiplication, and we're going to do division. And when anti-differentiating, or when doing anti-differentiation, either one of those, there's got to be an ing in there somewhere. When doing anti-differentiation, we divide by k. Okay? We divide by k. So when I take the derivative, I multiply by k. So whenever we go backwards and we anti-differentiate, we do the opposite, which is dividing by k. Again, that's a very nice general theme when it comes to the relationship between integration and differentiation. I'm going to use the words integration and anti-differentiation interchangeably. You should feel free to do so. They are essentially the same thing. So we're going to integrate f of x dx. And f of x, well, that's just e to the negative 21x dx. And this one is perhaps the most straightforward application of our rule yet. All that we're going to do is we are going to multiply e to the negative 21x by 1 over negative 21. Equals 1 over negative 21 e to the minus 21x. Again, technically, I'm going to go ahead and write it in green here because we have a plus c, but c equals 0 in this particular case. Okay, so just remember, in this particular problem, we're given that c equals 0. So really our answer is just this part in black, but it is, I urge you to develop the habit of writing plus c at the end of these indefinite integrals. I think that we have at least one more in this rapid fire round. Yes, we do have one more. This one is phrased slightly differently, but we're going to work through essentially the same process. Right in orange. Problem 9. And this one is phrased ever so slightly differently. Find the most general, and I'll explain what they mean in a second, antiderivative or indefinite integral. So just as I was saying, those two things are interchangeable. They say antiderivative or indefinite integral. An indefinite integral is just an integral where we don't have specific bounds. Okay, so sometimes we'll see an integral with like two values, like a to b. That's called a definite integral, and we'll do some of those shortly. If we don't have those bounds, then we don't have specific bounds, then this is called an indefinite integral. In this case, the function which we're given is 1 over x minus 4 over x squared plus 1 dx. So the most general antiderivative, this means that we're just going to give a plus c at the end of our answer. We don't know what c is, so c can be anything, which is why we're going to put a plus c instead of, like we did in these other problems, we just ignored it. Here we're going to leave that plus c at the end. That is literally the only difference between what we've been doing and what we'll do in this problem. So actually there are two rules here, one of which I'm seeing I wasn't expecting to give because I totally missed it, but here we are. But it's an easy one. It's easy once you know it. I mean, you know, to someone who's done it plenty, it's another fairly straightforward one. So the antiderivative of 1 over x dx, well, I'm going to also go ahead and write this as the antiderivative of x to the negative first dx. Notice that these two things are just the same. I haven't actually written anything fancy yet, anything new. This is the natural log of the absolute value of x. Okay, natural log of the absolute value of x. In fact, this is just the power rule, which we talked about in the first problem today. So here I said, well, we can't let n be 1 in this case, or negative 1, right? We had x to the n where n is not negative 1. Well, here we have x to the negative 1. So this is what happens in that case. The other rule, which will be relevant here, that second integral looks really scary, right? And I'll admit it's certainly a little bit frightening to me even. However, this one is of a very special form as well. Dx equals 1 over k arctan of kx plus c. If you prefer, you can write tan inverse of kx. These two things are the same, arctan and tan inverse. I prefer writing arctan because it makes it, we had a conversation someday about how arctan is not the same as 1 over tangent. That's why I like writing arctan. To me, that notation is more clear than tan to the negative first. But they technically mean the same thing, so whichever you're comfortable with. This is a very important identity, which in Calculus 2 becomes very important, in which you start to understand why this actually works. Here it looks kind of random and crazy, but there you really start to see why it matters, and you use it quite frequently. So this is an important one. But enough with the rules. Let's go ahead and start applying these bad boys. Well, the first thing that I'm going to do is notice that whenever I'm adding up two things within an integral, I can go ahead and split those up into two separate integrals. Okay, so I can split up this first integral into these two smaller integrals. This is very nice because, well, this first one, 1 over x dx, we just wrote out this rule, so that's just ln of x plus c. Okay, and now the second integral, what I can do to help me with this one is pull out the 4. Okay, remember the 4 is just the constant here, so I can bring constants out front of integrals if I like. That is almost always the first thing that I do whenever I see an integral. If I have a constant that I can pull out, I will usually go ahead and do that. Okay, so let's go ahead and move on. So that's ln absolute value of x plus c minus 4. Okay, so now this integral here, it looks like this is just our arctangent integral, where the role of k is being played by 1. I accidentally hit I accidentally put my iPad to sleep for a second there, so my B. So there's a nice little trick here, which we're going to use, and that is that whenever we have, so when we have 2 plus C's or more, 2 or more plus C's, we can combine them into 1. In other words, at the end of all this, we're only going to need to put 1 plus c at the end. Combine them into 1. And not into the number 1, into 1 plus c. So in this case, we're going to get ln absolute value of x. Now let me go ahead and simplify the second part slightly, so that becomes minus 4 arctan of x plus c. I don't need to write plus 2c. The reason for that is kind of philosophical, and in the interest of time, I'm not going to go into it here. I would love to talk about this with any of you in office hours. I'm sure if you Google it, you can find some nice explanations. But I would love to explain it to you some other time. But for now, I think I'm going to keep the focus on the problem solving. But please let me know, because I love that stuff. At any rate, we have found our antiderivative. Again, this is the most general form with a plus c at the end. Okay? All right. I think that might do it for kind of those ones that I really wanted to fly through. Yeah, I believe it does. So why don't we jump to 12? 12 is one that gave me a little bit of trouble, I will be honest with you. Let me get that burnt orange color back. I like that color. Let's go with this one. 12. So a driver, this one I'm going to take a minute to write out. I apologize. A driver, actually, you know what? I'm not going to go through and write out the full situation. Basically, there's basically 3 parts, and you don't need to know the actual situation to do the parts. So let me try and again be more time efficient. This one is about, I'll read it aloud for you here. A driver driving along a highway at a steady 60 miles per hour sees or 88 feet per second, sees an accident ahead and slams on the brakes. What constant deceleration is required to stop the car in 242 feet? To find out, carry out the following steps. So basically, they're giving us a procedure to follow to help us solve kind of this bigger problem with a nice real-world application. But as a pure mathematician, I say, screw real-world application. I'm kidding, of course. I am being facetious. Okay, so the first part which we're going to need to solve is the initial value problem. They've kind of broken this up into 3 steps for us. So we need to solve this equation. The second derivative of s with respect to t is negative k, where k is a constant, with ds dt equals 88. So the first derivative of s with respect to t equals 88, and s equals 0 when t equals 0. I think part of what threw me off the first time, whenever I first saw this problem, was that these 2 things both have to be true whenever t equals 0. When I first did this, I thought that only s equals 0 when t equals 0. But we also need that ds dt to be 88 whenever t is 0. So the way that we're going to start, we're going to integrate or differentiate negative k. Okay, we're told here in this first step that the second derivative of s with respect to t is negative k. So if we take the antiderivative, so ds dt is going to be the antiderivative of the second derivative Okay, so if I go down 2 derivatives and then I undo one of them, well, then I'm back at just the first derivative. We are told that the second derivative of s with respect to t is negative k. So this is the integral of negative k dt. And there's another rule. Well, actually, this is just a special case of the power rule, really. So let me I'm going to write this in kind of a funny way for you. I can rewrite this as negative k times the integral of t to the 0 dt. You'll agree with me that t to the 0, this is just 1. But by writing it this way, it allows me to very nicely just use the power rule for antiderivatives. So the power rule says I'm going to raise the exponent by 1. Okay, so times t to the first over, and then I'm going to divide by my new exponent. So over 1 plus c. The reason that I'm using t here instead of x is that my variable in question is t. Okay, whatever your variable is, that's how it's going to work. So basically, what I'm saying here, this is a fancy way of saying that the integral of k dt is always just k times t for any constant. Okay, so where k is a constant, if I integrate any constant, I just get that constant multiplied by the variable. That's all this is saying. For example, the integral of 2 dx would just be 2x. All right, so this negative k times, this is just negative kt plus c. Okay, so now I have that dsdt equals negative kt plus c through our string of equations. And I'm told in the problem that dsdt equals 88 whenever t equals 0. So that means that 88 equals negative k times 0. Okay, remember, dsdt is 88 when t is 0. So negative k times 0 plus c. So that means that 88 equals c. Okay, so usually we just have this variable plus c at the end. But with a bit more information like we've been given here, we can actually conclude exactly what c has to be. So what this means in general then is that dsdt, a general formula for it, is negative kt plus 88. Okay, so this gives us, so this is our solution to the initial value problem. The initial value problem, whenever you see something like that, such as this problem here, this is kind of the initial value problem, what I put in a box here. The answer to that is going to be a function, is going to be, in this case, it's our function dsdt. Okay, so you want to find a function that has the given derivative. All right, so in this case, we need to find a function whose second derivative is negative k. All right. So we've solved this first initial value problem. Part B, or they actually call it part 2, but I'm going to call it part B, says find the, oh wait, excuse me. We're not done, because I said we have to find a function s, but all that we have found is dsdt. So now, to find s of t, we antidifferentiate dsdt. Okay, so we're going to antidifferentiate one more time to get back to our original function. There we go. I knew something fell off. So the integral, so s of t is going to be the antiderivative of ds dt. Okay, and we know that ds dt is negative kt plus 88, all of that dt, remember, to include your d whatever variable. Okay, well, negative kt, we can integrate this nicely as the integral of negative kt dt plus the integral of 88 dt. Okay, well, negative k is a constant here, so that's negative k integral of t dt plus 88 integral, I'll write it again this way, t to the 0 dt, although really this is just a 1 here. And so, let's see, negative k integral of t dt. Well, the integral of t dt is t squared over 2. Okay, this is just power rule. Remember, this is t to the first power. So this is negative k times t to the second power over 2. Raise the exponent by 1 to get t squared. Then divide by that new exponent, so I'm dividing by 2. And as we discussed above, we get an 88t here. Okay, 88 times the integral of 1 dt just gives me 88 times my variable. And we need a plus c at the end. Now we also know that s equals 0 when t equals 0. Okay? And we just found a formula for s, right? S of t is equal to this formula, which means that 0 equals k times 0 squared over 2 plus 88 times 0 plus c. And that means that c equals 0 now, right? Because I just have 0 equals 0 plus c. So s of t is negative kt squared over 2 plus 88t. I just rewrote the line above, line up here, replacing c with 0. So this is our solution to our initial value problem. We found a function s satisfying all of the conditions given to us here in our little box. Okay, now we're going to jump to part B. And part B wants us to find the value of t that makes ds dt equal to 0. And it gives us kind of a hint that the answer will involve k. So our answer won't just be some number, it'll be a formula in terms of k. Well, not only, I shouldn't say only. Will involve k. Okay, well, we have a nice formula for ds dt. We see that ds dt equals negative kt plus 88. Okay, so ds dt equals negative kt plus 88. So we set this equal to 0, and I get 0 equals negative kt plus 88. And then it's very much just straightforward. I get negative 88 equals negative kt. Divide both sides by negative k, and you get 88 over k equals t. Okay. Part C then asks, find the value of k. And this one I will talk through briefly and then not actually do, because it looks like it might involve a bit of messy computation, which you are perfectly capable of, and I think wouldn't be particularly enlightening. You know how to do it. Not easy per se, but it will just be some algebra and such. For the value of t found in step B. Value of t found in B. And that value was t equals 88 over k. So find the value of k that makes s equal to 242. Well, s is negative kt squared. Negative kt squared over 88, right? No, over 2 plus 88t. Over 2 plus 88t. And so what you'll do is you will set how do I want to write this? You will replace s here. We want s to be 242, so write 242 equals all of this stuff. And then plug in plug in t equals 88 over k, and then you just solve for k. At that point, you'll have 242 equals something with only k's in it, and then you can just solve it. All right. So I will leave you to put the finishing touches on that one. Problem 13. This one is reminiscent of one of my favorite derivative type problems. So we're going to be given some information about some antiderivatives and be asked to conclude some more information using some of our new fun rules. Functions f and g are integrable, and okay, so we're going to be given a few pieces of information here, so let me make them nice and clear. The integral from 2 to 4 of f of x dx equals -4. The integral from 2 to 7 f of x dx equals -8. And the integral from 2 to 7 of g of x dx equals -5. Okay, so these are going to be the three pieces of information which we're going to be coming back to throughout this problem. So let's go ahead and start out with the computations. Part A asks us to find the integral from 4 to 4 of f of x dx. So now we're moving into definite integral land because we're starting to see some bounds on these integrals. Okay, so you see we've got 2 and 4, we've got these bounds on our integrals, and that's what makes these definite integrals. So first we're asked to evaluate the integral from 4 to 4 of f of x dx. The rule which is going to be relevant here is the following, which is simply that the integral from a to a of h of x dx equals 0 for any a. H of x, of course, is just some function, and what this is saying is that if I integrate from one point up to the same point, right, so the important thing here is that my two bounds are the same, that is always going to be equal to 0. Which makes sense intuitively. I won't go into great detail here, but let me sketch a very quick picture for you. If I wanted to find the area under the curve, say from x equals 4 to x equals 4, well then all that I'm asking for is the area under the curve, literally of just this one segment, right? And the area of one line segment is 0. A line segment has no area. So that's the basic idea there in terms of why that is equal to 0. Again, it could be any value. We're not picking on 4 here. That would certainly be the case for any particular value. Part B asks us for the integral from 7 to 2 of g of x dx. Okay. So I should mention this first part, it doesn't even matter what f of x is. We didn't have to use any of these three pieces of information. That is always going to be true. Now these other parts, we're going to have to rely on that information. So here we are asked to find the integral from 7 to 2 of g of x dx. Well, let me see. I don't have the integral from 7 to 2 of g of x dx, but I do have the integral from 2 to 7 of g of x dx. So notice here I have 7 on top and 2 on the bottom with g of x. And this problem asks, can I get them both on one screen? Yes. this problem is asking for the integral from 7 to 2, and we're given the integral from 2 to 7. So these two things are not the same, however they are closely related. The rule, so in general, is that the integral from a to b of h of x dx is the negative of the integral from b to a of h of x dx. Okay, in other words, if I flip the bounds, then I introduce a negative sign. So in this case, this is going to be the negative of the integral from 2 to 7 g of x dx. Well, we know that the integral of g of x dx is negative 5 from 2 to 7. So we just get a negative there, which means that our answer is 5. Okay, the integral from 7 to 2, or excuse me, from 2 to 7 is negative 5. So we multiply that by negative 1. Part C, there it goes all the way to F here. We'll see. Maybe we'll do all of them. Maybe we'll stop at some point. Part C, I guess this is kind of another quick lightning round. We are asked to integrate 3g of x dx. I've actually kind of mentioned the rule here which we use, but I'll go ahead and write it out explicitly again. And this says that the integral from a to b of k f of x dx is equal to k times the integral from a to b of f of x dx. That should be, I'm going to change the f's to h's just to be consistent. And because we already defined f, it's one of the things defined in this problem. However, it's just, yeah, it doesn't actually matter. In other words, I can just pull that k out front. So in our particular problem, that means that this is equal to 3 times the integral from 2 to 7 of g of x dx. Okay, 3 is my constant here. The integral from 2 to 7 of g of x dx is negative 5. So this is 3 times negative 5, and that is negative 15. Okay. Notice the one thing I will say about this real quick before we move on to part D is that the 3 here is not inside the function g, right? We're multiplying g by 3. The 3 is not g of 3x, it's 3g of x. That is very important. We will learn how to deal with things of the other form later on. I think that you'll probably do it here in Calc 1. If not, you will certainly do it in Calc 2, but I'm pretty sure that we'll get to it here. Okay, part D wants us to integrate from 4 to 7 f of x dx. Okay, so if we look at what we have, I know what the integral from 2 to 4 is of f of x dx, and I know what the integral from 2 to 7 is of f of x dx. But I don't know 4 to 7 explicitly. But what I can do, and this is the rule for this particular problem, for this part of the problem, is that the integral from a to b of h of x dx plus the integral from b to c of h of x dx equals the integral from a to c of h of x dx. Okay, so if I look at this, for example, on a number line, this is saying that if I go from a, b, c, this is saying if I go from a to b, and then plus what I get from b to c, well, that's the same as if I just go all the way from a to c in one jump. Okay, the area doesn't change, which should make sense. If you think about it, if you draw a picture and you remember that really the goal here is to compute area, I think that things should fall into place. Notice the important thing is that we have the upper bound here, so b is the upper bound and then b is the lower bound. Okay, if b was not in these, for example, I couldn't say that the integral from a to b plus the integral from from a to c is equal to the integral from b to c. Okay, the important thing is that really it goes with this picture. First, I'm going from a to b, so b is my upper bound because it's the right endpoint, or then I'm going from b to c because I'm starting at b and moving to c. In this particular problem, this is helpful because what I can do is I can say, well, actually, let me rewrite this rule. So the rule further states then, if I split this up, this tells me that the integral from b to c of h of x dx is equal to the integral from a to c h of x dx minus the integral from a to b h of x dx. Okay, all that I've done here is I subtracted over that first piece from the rule, subtracted it over to the other side, and I now have a formula for the integral from b to c. So what this means in terms of our particular problem is that if I want the integral from 4 to 7, I can do the integral from 2 to 7 and then subtract out the integral from 2 to 4. This is helpful because these integrals on the right are the two integrals that I know. I didn't give myself enough room here. I know the integral from 2 to 7 of f of x. That's -8. And the integral from 2 to 4 of f of x is, oh, I'm going way too far. From 2 to 4 is -4. So minus 4 equals -4. Okay, this arrow is not very clear. I want this arrow to go like this. Okay. And so this might look kind of complicated with all these numbers and variables, and I apologize for going kind of quickly, but basically it's very intuitive if you sit down and think about it. You can break up the intervals just like you would expect yourself to. Okay? You can break up the integrals exactly like you would expect based on these bounds. Okay. So, in fact, let me sketch a picture of this real quick. I do think this is probably worth sketching a picture because I feel like all that talking was a bunch of abstract nonsense. I'm just going to sketch a parabola because that's like the first picture that comes to mind. And let's label our points 2, 4, 7. So, I don't know, 2, 4, 7. Okay. Well, the area, so let me just, so what the rule is saying is that the area from 2 to 7 is equal to the area from 2 to 4. So area from 2 to 7 equals area from 2 to 4 plus area from 4 to 7. Which makes perfect sense if we look at our picture. If I want the area, the total area underneath this this graph from 2 to 7, well, then I can compute the area from 2 to 4, and then add up the remaining part, the area from 4 to 7. So that's the idea here, and I hope that one of these ways of thinking about it makes some sense. Whew, okay. So we now have part E. Part E asks us for the integral from 2 to 7 of g of x minus f of x dx. Okay, well, as you would expect, I'm not going to write out a fancy rule for this, but just as you would expect, this is the same as the integral from 2 to 7 of g of x minus the integral from 2 to 7 of f of x. Okay? So I can split up this integral just like we've done before whenever we were adding and subtracting things. You can split up the integral. We can do the same thing whenever we stick bounds on it. That's basically what this is saying. Okay? I'm actually going to go ahead and I think leave the rest of this problem to you in the interest of time. For that part here, all that we do, we already have these two values, so we can just plug our values in. So I think that there are two more which I'm going to try and get through here. Yeah, that seems good. Problem 20 is next up. And here we want to find the function y of x satisfying, so the equation we want it to satisfy, this is what's called a differential equation. Mackenzie's probably mentioned in her videos how much she loves differential equations. She is a differential equations nerd, and it is awesome. I truthfully have not studied differential equations very much, but she absolutely loves them. So we want to find the function y of x, whose derivative is 8x minus 7, and which satisfies y of 8 equals 0. Well, what we notice is that y of x, well, to get y, we can anti-differentiate the derivative. Okay, so that's the integral of 8x minus 7 dx. Right, we're told that dy dx is 8x minus 7. And this, we can just use, this will be a fairly straightforward power rule, or I guess anti-power rule, depending on what you want to call it. So this will be the integral of 8x dx minus the integral of 7 dx. Okay, the integral of 8x dx, well, that's going to be 8x squared, and now I have to divide by 2. Okay, so raise the exponent by 1, divide by the new exponent. And this 7, you'll recall, whenever we integrate a constant, all that happens is we stick the variable behind the constant. So 7 becomes 7x, and we get a plus c at the end here. And in fact, I can rewrite this because 8 over 2 is just 4, so this becomes 4x squared minus 7x plus c. Okay, so this is our general formula for y of x. But we have more information, which is that y of 8 equals 0. So, since y8 equals 0, we can solve for c. And the way that we do that is I set 0 equal to 4 times 8 squared minus 7 times 8 plus c. And then, oh, come on, Bailey, you can do this. That gives me 0 equals 8 squared is 64. 2 times 64 is 128. So that's going to be 256 minus 56 plus c. So 0 equals 200 plus c. And negative 200 equals c. So in conclusion, y of x equals 4x squared minus 7x minus 200. Okay, all that we did was we went up here, we had our formula for y of x, and then we figured out exactly what c was, and we plugged that in to get our final formula. The last problem for today is the final problem on the homework, and it's a very similar style, but it involves trig. We've hardly done any trig. I think we had one trig problem in this. So I had to get a little bit more trigonometry in here. Solve the following initial value problem. So I'm going to note here, initial value problem. So what we're given is dr d theta equals negative pi sine of pi theta and r of 2 equals 2. So I'm going to note here, this is the exact same set of instructions as the previous problem. It looks different. The first problem says, find the function y of x satisfying these two conditions. So whenever we get an initial value problem, all this is saying is find r of theta satisfying blah, blah, blah. In this case, these two equations. So that's what it means whenever it says solve the following initial value problem. It just means find the function, in this case r, satisfying these two conditions. Well, just like before, we're going to start by anti-differentiating the derivative. So r of theta is going to be the antiderivative of dr d theta. And we know that dr d theta is negative pi sine of pi theta d theta. Okay, and I don't think that I've written out a rule for sine yet. So let me go ahead and give ourselves that rule. And that is that the antiderivative of sine of kx dx is going to be 1 over k times negative cosine, that looks like a minus cosine, times, let me put a dot to be clear, times minus cosine of kx. To check this, let's go ahead and take the derivative of that. So d dx of this equals, okay, so I've got 1 over k as a constant. The derivative of cosine is negative sine. So the derivative of negative cosine is positive sine kx. And then I need to multiply by k because that's the derivative of the inside, so that's chain rule. And this is sine of kx, which is exactly what we want. Okay, so let's go back up to our problem here. What I can do first is pull the negative pi out front because that's a constant. Sine of pi theta d theta. Okay, and let me continue down here. So this is, I've got a minus pi times, now when I use my rule, I see that I'm going to multiply that by 1 over pi. Times negative cosine of pi theta. Okay, and excuse me, I should have written in my rule, there should of course be a plus c at the end. Okay, so there goes a plus c at the end here. And now I can simplify this a bit. I've got pi, then I'm dividing by pi, and I have a negative. I've got two negative signs, and so this actually just comes out to cosine pi theta plus c. Is that right? Ah, yes, it is right. Okay. Yes. I doubted myself for a second. Okay. So this is r of theta. But we also know that r of 2 equals 2. So 2 equals cosine of pi times 2 plus c. Well, cosine of 2 pi, that's just 1 because we are all trigonometry experts, right? If not, we're getting there. Okay, so 2 equals 1 plus c, 1 equals c, which means that r of theta is cosine pi theta plus 1. And there we go. Well, that does it for this video. I hope that you found it helpful. I kind of took a different approach to this one, right? I did kind of a lot of problems and I did them a bit more quickly. I hope that that's helpful. I don't know.